Welcome to Standard Uncertainty and Instrument Tolerances. This is part 3 of a 4-part video series. Part 1 being Sig Figs and Measurement Uncertainty. Part 2 being Accuracy, Precision, Error, and Difference. Part 3 that we're doing now is Standard Uncertainty, aka Standard Deviation, and Instrument Tolerances. And Part 4 is Combined Uncertainty, also called the propagation of error. And you'll find links to all of these videos at the website www.chemrat.com. So let's get started. A brief overview of what we will cover in this video is a very short review of systematic versus random error, uncertainty, standard deviation, and the Gaussian distribution, expanded uncertainties and confidence levels, and instrument tolerance. Now, by way of a very brief review from video part 2, there are 2 types of experimental error. We said systematic errors, also called determinate errors or type B errors. They are one-sided errors and they will shift or bias results, always making the results too high, giving rise to positive error, or too low, giving rise to a negative error, but not both. And we have random errors, indeterminate errors, type A errors, also called two-sided errors, causing measurements to fluctuate above and below a central value, causing both positive and negative deviations from a mean value. Now, determinate error often can be detected and corrected by standardization or calibration, etc. Random errors can be reduced, but never eliminated, but they can be quantified using statistics. So the various types of experimental error that we've been discussing will create uncertainty in our measurements and in the results calculated from those measurements. Now, the data on the next few slides was adapted from the website below, which was quite helpful. So how do we quantify this uncertainty? Well, we mentioned that although random errors can never be completely eliminated, is the good news, they can be quantified. Now just consider the following analogy. Let's say you had a crude liquid dispenser like this. Each time you pumped it, it delivered a certain volume. Let's determine the precision in delivering a liquid volume of, say, 3.5 mils from this automatic dispenser. You could repeatedly dispense the liquid into, say, a 10 mil graduated cylinder and measure the volume. And let's say these were your results. First trial, 3.9 mils. Second trial, 3.5 mils. Third trial, 3.7 mils. Fourth trial, 3.4 mils. And fifth trial, 3.5 mils. A good estimate of the average volume delivered is the arithmetic average of the results, which you can see is calculated by adding up the individual volumes to get the total volume and dividing by the number of volumes delivered. 5. The average is 3.6 mils. And the symbol for that is called X bar. Now, X bar is the symbol for the arithmetic average, sometimes called the sample mean. Now, if you had dispensed this many times, say at least 20 times, then the symbol would not be X bar, but rather mu, and that is called the population mean. So what's the uncertainty of our measurement? We could report the maximum uncertainty as plus or minus 1/2 the range. So we take the difference between the maximum and minimum values, maximum being 3.9, the minimum being 3.4, here it is here, that'll be 0.5, divided by 2 to get half, and that's plus or minus 0.25 mils. So we could report the average volume as 3.6 plus or minus 0.3 mils. Note that the precision of the uncertainty matches the precision of the calculated value. They must be the same. So this maximum uncertainty is also called the range method. It tends to overestimate the uncertainty. It's called the maximum uncertainty. What we want to report is the most probable uncertainty. Another way to estimate uncertainty is to report the average deviation. So we would average each volume's deviation from the mean. Recall the mean x bar is 3.6 mils. So here each deviation would be the reading 3.9 minus the average 3.6. In this case, the deviation is 0.3. In the next case, we have 3.5 minus 3.6, giving us a deviation of negative 0.1, and so on for all 5. Add these up, divide by the number of deviations, and we get a value for the average deviation to be, well, 0. Well, it turns out that the average deviations can't be used as the uncertainty estimate because it gives us a 0. And in fact, the average deviation will always be 0 for any set of measurements because the deviations with the positive sign are always canceled by the deviations with the negative sign. Well, then you ask, well, can't we get rid of the negative signs? Well, we can if we take the average of the absolute value of the deviations. So here, instead of putting the deviation, we're going to put the absolute value of the deviation. So 3.9 minus 3.6 is still 0.3, but here where we have 3.5 minus 3.6, instead of getting negative 0.1, the absolute value will be plus 0.1. So any of these negatives become positive. We'll add these absolute values of the deviations up, divide by the number of them, and this time we'll get 0.16 mils as the average deviation of the absolute value of the deviations. And recall that this is, well, a little lower than we had for the maximum deviation. The value on the previous slide was 0.25 mils. Now, it turns out that the average deviation, 0.16 mils in this case, is a legitimate estimate of uncertainty. However, the standard deviation has proved more successful in making statistical predictions, and we're going to look at the standard deviation next. So the standard deviation turns out to be the best measure of the uncertainty of a group of samples. Now, rather than taking the absolute value of the deviations, we will now square the deviations. That will make all the numbers positive, and that way they won't add to 0. But then we'll have to remember to take the square root of that sum so that our uncertainty that we calculate will have the same units as our measured value. So our measured values are in milliliters. We can't have the deviations in milliliters squared, hence the square root. So this is the formula for standard deviation. S of x, standard deviation of a sample, is equal to the square root of the sum of the deviations squared divided by n minus 1. We'll talk about the n minus 1 in just a minute. Let's look at the deviations squared. So here we have the formula for the deviation, the individual value minus x bar. Recall that x bar was 3.6 for this sample group. So here the first sample is 3.9 minus 3.6. The deviation is 0.3. We square that and get 0.09. That's the deviation squared. In the second trial, we had 3.5 mils. That's x sub I minus 3.6, which is the average, to give us a difference of negative 0.1. But when we square that, we get plus 0.01. So it makes it positive. And so it is with the rest of the values. So here then are the sums of the squares of the deviation. We divide that by the number of samples, 5, less 1, and take the root of that, and the answer is 0.20. Now 0.20 is a little bit bigger than 0.16 mils. If you recall, that was the average deviation of the absolute values of the deviation. And it was a little bit less than 0.25, which is the maximum deviation we calculated by the range method. Now, when the sample size is less than 20, the sample standard deviation is calculated by dividing by n minus 1. And when the sample size is large, greater than 20, then the standard deviation of the population, sigma x, is calculated by dividing by n. So why the difference? Well, it turns out that the standard deviation of small sample sets tends to underestimate the population standard deviation. For example, when the number of samples is only 2, the underestimate is about 25%. And when the number of samples reaches about 6, the underestimate has reached about 5%. And hence we have different formulas for sample standard deviation and population standard deviation. So it turns out as the sample size increases, as n increases, the sample average, x bar, approaches the population average, mu. Likewise, the sample standard deviation, s of x, approaches the population standard deviation, sigma x. So you won't want to be calculating standard deviation by hand very often. So I've included here a set of instructions for calculating the sample standard deviation using the Sharp calculators. Go ahead and calculate the sample standard deviation for this data set, and you should get a value of 0.2. I'll leave it with you to try. The result is we want to report the best estimate plus or minus an uncertainty. In our example then we could state the average volume delivered was 3.6 mils with a standard uncertainty or standard deviation of plus or minus 0.2 mils, and it's written in this fashion. Histograms and the normal distribution. So if we were to continue taking additional measurements, the random uncertainty invariably displays a predictable pattern. When the volumes of 10 consecutive measurements were made, they are plotted as a frequency distribution, also called a histogram, and the shape resembles a bell curve. So here's the data. So a volume of 3.4 mils was measured once. Here's 3.4 mils occurring once. 3.5 mils occurred twice, and 3.6 mils occurred 3 times. 3.7 mils occurred twice, and so on. If we had not taken just 10 but many more measurements, the histogram would resemble the bell curve even more. It would start to look continuous in this fashion. In fact, for very large numbers of measurements, the histogram would be indistinguishable from a continuous curve. This curve is called the limiting distribution, and for most of the experiments in the lab, the limiting distribution will be a bell curve, which is also known as the normal curve or Gaussian distribution. The nice thing about histograms is that we can see the mean value of our measurements. In our example, clearly the mean is 3.6 mils. Could we find the standard deviation from a histogram? Well, if we were to calculate the standard deviation of all the 10 values plotted here, we would find the formula gives us 0.15 milliliters. And if we were to draw vertical lines at 3.6 mils plus or minus 1 standard deviation, that is plus or minus 0.15 mils, we get values of 3.75 to 3.45. We see that 3.5, 3.6, and 3.7 are within the range defined by 1 standard deviation. And we note that 7 of the 10 measurements obtained are one of these 3 points. So 3.5 occurred twice, this one occurred 3 times, that's 5, and 2 more here. 7 of the 10 measurements fall within this range. In other words, about 70% of our measurements fall within the range of plus or minus 1 standard deviation. This is not a coincidence. It is a property of random values in the normal distribution that 68% of the measurements will lie within 1 standard deviation, either side of the mean. And since our distribution comes close to a normal distribution, our result of 70% is close to the theoretical value of 68%. The normal or Gaussian distribution is so important that we should talk about it in a little bit of detail. So in the normal distribution of an infinite population, that is a lot of measurements, the percentage of measurements that fall within a given number of standard deviations from population mean is shown in this chart. So the y-axis, which is not numbered here, it represents the relative frequency of a measurement's position on the chart, and the x-axis shows the distance from the population mean in units of standard deviations. Standard deviations from the mean. Now, there are many markers we could look at, but the 3 most important at least in chemistry, are listed here, and let's discuss these. So random measurements fall within plus or minus 1 standard deviation, plus or minus 1 standard deviation, 68.3% of the time. Another way to state that is if we looked at the total area under the curve, the area between plus 1 and minus 1 standard deviation represents 68.3% of the total area. Random measurements fall within plus or minus 1.96. So this is plus 1.96 and minus 1.96, just below 2 and just above negative 2. And that occurs 95.0% of the time, or 95 times out of 100. And random measurements fall within plus or minus 3 standard deviations, 99.7 times out of 100. So let's look at this again. It is important. There is a 68% probability that randomly distributed results will fall within plus or minus 1 standard deviation from the mean. And that means that 32%, or 320 out of every 1,000 readings, would normally fall outside, above, or below 1 standard deviation from the mean. So 68% probability on a reported result is not a high level of confidence. We commonly in chemistry report numbers at the 95% confidence level. So we can see that there is a 95% probability that randomly distributed results will lie within plus or minus 1.96 standard deviations from the mean. And then only 5%, or 5 in 100 readings, will normally fall outside these limits. Let's talk about expanding our uncertainty and coverage factors. So earlier, when we only had the first 5 volumes measured, we reported the average volume was 3.6 mils with a standard uncertainty, or standard deviation, of plus or minus 0.2 mils. We called plus or minus 0.2 mils the standard uncertainty because it was 68% probable at the plus or minus 1 standard deviation limit. Now, often in chemistry, our measurements are in fact reported at the 68% confidence level, probability of plus or minus 1 sigma. But then the final result is reported at the 95% confidence level rather than the 68% confidence level. Now we can convert between the 68 and 95% confidence levels because we know their relative sigma values, simply a factor of 1.96 between them. So the expanded uncertainty at the 95% confidence level in this case would be 0.2, which was the 68% confidence level uncertainty, times 1.96, and that gives us a value of 0.39 mils, or 0.4 mils plus or minus. So the multiplier 1.96 is called a coverage factor, often given the symbol K because it expands the uncertainty coverage from the 68 to the 95% level. So we would thus report the average volume to be 3.6 mils plus or minus 0.2 at the 68% confidence level. We would also report the average volume to be 3.6 plus or minus 0.4 mils at the 95% confidence level. Relative standard deviation, also known as coefficient of variation, really important tools in the chem lab. So in the same way that percentage error or relative error allows us to compare the accuracy of different tests, well, likewise the percent standard deviation or relative standard deviation allows us to compare the precision of different tests. And percent RSD is calculated similar to percentage error. So recall that percentage error is simply the absolute error divided by the true value times 100%. Well, percent RSD is the absolute or actual standard deviation divided by the mean times 100%. So in our previous example, the standard deviation was plus or minus 0.2 mils, and the average was 3.6 mils. So the percent RSD is 0.2 divided by 3.6 times 100%, and that's 6%. Now here's an important rule of thumb to keep in mind as you work in the lab. The percent RSD for replicate analysis should be less than 2% for instrumental analysis. Should be less than 0.5% for classical chemical analysis using volumetric glassware and the analytical balance. A good rule of thumb to keep in mind. Let's get some practice. A student measured the temperature in a cold water bath using 5 different digital thermometers. And here it's the temperatures. Using the first thermometer, she measured 11.9 degrees C. The second thermometer read 11.6 degrees C. The third measured 11.8, then 11.9, and 12. I'd like you to calculate the mean temperature, the standard deviation of the mean temperature, and the percent RSD. Then I'd like you to state the mean temperature and its standard uncertainty and the confidence level for this uncertainty. State the mean temperature and its expanded uncertainty at the 95% confidence level. So I'll let you work that out, pause the video, and then when you're ready, come back and check your answers. All right, so here's how that should work out for you. X bar you would find to be 11.8 degrees Celsius. The standard deviation, 0.152, which rounds to 0.2 degrees C. And the percent RSD is calculated as the absolute standard deviation divided by the mean, 11.8 times 100%, you'll be 1.3% RSD. Now you might ask, how many sig figs should I report in a percent RSD? It's very simple. Only one sig fig if you are greater than 2% RSD. If you're less than 2% RSD, then you can use 2 sig figs and no more. Now think about it. If the scatter is greater than 2% RSD, who really cares whether it's 3.2 or 3.5? The point is it's around 3. If you, however, have less than 2% RSD, then it would be appropriate to have 2 sig figs, but no more. So the standard uncertainty, 11.8 plus or minus 0.15, that would be at the 68% confidence level. I was asking you what that standard uncertainty is. It's a 68% confidence level, which would round to 11.8 plus or minus 0.2. Notice I'm keeping consistent precision for the uncertainty and its value. So the expanded uncertainty will be 0.15 at plus or minus 1 sigma, multiplying by 1.96, which is the coverage factor or K value to convert between the standard and the 1.96 uncertainty level. So that would be plus or minus 0.3. So I would state that as 11.8 plus or minus 0.3 degrees Celsius at the 95% confidence level. So you may be wondering, how many sig figs should I report in an uncertainty? Well, first of all, it's really imperative that you report results with the same level of precision as the uncertainty. And then report uncertainty to 1 or at most 2 sig figs. And I'll explain with some examples here. First of all, 657 plus or minus 5. Well, that's correct. You see, the most precise digit in the uncertainty and in the result are equivalent. They're both in the ones column. That's appropriate. What about 657 plus or minus 0.5? That's not right. You see, if the precision is this good, then you should report the result to 1 decimal as well. So you might report 657.2, for example, plus or minus 0.5. Notice the precision of the uncertainty and the result are consistent now. What about 6.57 plus or minus 0.05? Yeah, that would be right, because the most precise digit in the uncertainty and the result are both in the second decimal place. What about 6.657 plus or minus 0.5? Well, that's terrible. If the uncertainty is in the first decimal place, then you can't report a result that has 3 decimal places. You should be reporting something like 6.7 plus or minus 0.5 first decimal place for both uncertainty and result. How about this last one? 96.57 plus or minus 1.4.
Well, that's not right either. You see, if the uncertainty is reported in the first decimal place, you can't report a result to 2 decimal places. So instead, you should report 96.6 plus or minus 1.4. This is now consistent. Or 97 plus or minus 1. Now I've introduced another variant here. How many sig figs should I actually report? 1.4 has 2 sig figs, 1 only has 1. Well, uncertainties are occasionally reported with 2 sig figs, as in this example, 2 sig figs and 1.4. If the uncertainty is for a standard reference value, you might see this in the literature or a handbook derived by many experimenters, or in your case, with your data, if the first sig fig on the uncertainty is 4 or less. Here's the first sig fig in the uncertainty. It's less than 4. In such a case, it's appropriate to carry 1 and only 1 more sig fig, a total of 2 sig figs in the uncertainty. Now, you might ask yourself why. Well, think about it. If the uncertainty is 1.4 and we do drop the 4, the 0.4 out of 1.4 is approximately 1/3. So we're discarding about 30% of the magnitude of this value. Okay, what about 2.4? 2.4 can be reported as an uncertainty because if we were to drop 0.4 out of 2.4, that's about 1/6 the total magnitude of 2.4, which is about 17%. So let's keep 2 sig figs. What if this number was plus or minus 3.4? Well, think about it. If we dropped 0.4 out of 3.4, well, it's a little more than 10%. It's actually 12% we'd be discarding, so let's keep it. What about if this was plus or minus 4.4? In such a case, we'd also keep 2 sig figs. If we discarded 0.4 out of 4.4, it's a little less than 10%. It's actually 9%. But the rule is that if the first sig fig is greater than 4, say this was 5.4, we would only report 1 sig fig. And if you think about it, if you had 5.4 and you dropped 0.4 out of 5.4, it's a small amount. It's about 7%. Now you might say, well, 7% is a lot, but remember, these are not exact numbers. These are just most likely, most probable estimates. So the rule is 1 sig fig unless your uncertainty has a 4 or more in the first sig fig of the uncertainty, in which case carry 2, but no more than 2. In any case, ask yourself, does the precision of the uncertainty realistically reflect the precision of the instrument, the measurements, and the mean? With some practice, this will make some sense. Also, just another note, don't mix notations. That is, don't write a result in scientific notation and then write its uncertainty or error in common notation or vice versa. Total uncertainty from random and systematic error. Now we learned that random error can be diminished by doing many replicate analysis, and that eventually the sample mean, x bar, becomes the population mean, mu. And mu will be the true value, now hear me here, it'll be the true value provided that random error is the only error present, whereas determinate or systematic error will bias or shift the results. So take a look at the diagram, and as we do, let's think back to the volume of liquid dispensed by the automatic dispenser into the graduated cylinder. The average of 5 measurements was 3.6 plus or minus 0.2 mils. So if we took many measurements, represented by these dots, we would find that the average might come out to 3.6 mils. So after many replicates, the sample average x bar would approach the population mean, mu, which we're hoping is 3.6. But now let's say that the graduated cylinder is reading 0.2 mils too low. So all of our readings should have been 0.2 mils higher, which means the true volume would have been 3.8, actually up here. So the sample average was shifted or biased to the left due to systematic error, in this case due to poorly calibrated labware. So uncertainty in our results, as it turns out, is often a combination of both random and systematic error together. So what about single measurements? You know, we can't calculate a standard deviation for only one measurement because there are no deviations to measure. So instead we're going to look at what's called instrument error or tolerance. So in many cases we do not replicate measurements. We might weigh a sample only once. We pipette one aliquot into one volumetric flask. We make one dilution. And so the built-in error or built-in uncertainty in our labware will introduce uncertainty into our final results. And although these uncertainties or errors are biasing, that is, they operate in only one direction, because the direction is unknown, they can be treated as if they were random. So here's a general rule for uncertainty. Instruments provided by reputable manufacturers have an uncertainty not greater than plus or minus 1/2 the smallest division on an analog scale, or plus or minus 1/2 of the final digit on a digital scale. So let's consider some examples. Say the common wooden or plastic ruler with 1 millimeter divisions. The instrument uncertainty is not greater than 0.5 millimeters, which is 1/2 of the smallest division. Let's consider the standard alcohol laboratory thermometer. It has 1 Celsius degree division, so in absence of information from the manufacturer, it should have a built-in uncertainty of not greater than plus or minus 1/2 a Celsius degree. Now, literature says that digital pH meters uncertainty is typically plus or minus 0.02 pH units. And uncertainty on digital top-loading electronic balances, well, it varies with the price and with the precision, but in absence of manufacturer specification, we would assume the uncertainty to be plus or minus 1/2 of the final digit. So for example, if the mass was reading 24.16 grams, then the uncertainty would be half of the last digit would therefore be plus or minus 0.005 grams. So these instrument uncertainties are often referred to as tolerances. They define a maximum range within which the true value should lie. And instrument tolerance is sometimes termed maximum allowable error or maximum uncertainty. Now be careful not to confuse tolerance with reading uncertainty. Remember, reading uncertainty was our best estimate in reading the last Sig Fig from an analog scale. Tolerance has to do with uncertainty within the instrument reading itself, not our interpretation of it. So here is a list of tolerances for Class A laboratory glassware, for pipettes, for volumetric flasks, for graduated cylinders, and burettes. So for example, if you had a 15 ml Class A transfer pipette, we're saying that the tolerance is plus or minus 0.03, which means the manufacturer pretty much guarantees that the true volume delivered when operated properly will be somewhere between 14.97 and 15.03. Now this information can be taken from laboratory suppliers' catalogs. It can be taken from analytical chemistry textbooks. You can get it from the internet. The point is that manufacturers will strive to produce their products consistent with these standards, and therefore we can use these with confidence. Just to note that Class B glassware typically has double the tolerance of Class A glassware. And as a note, I said it on the previous slide, but I just want to point out again, the error or the uncertainty that arises from the tolerance of an instrument is biasing, is determinate. It's either always positive or always negative, but since we don't know the direction, we can statistically estimate the error as if it were random. So we want to obtain a standard deviation from the tolerance. Remember that the tolerances are the maximum uncertainty ranges. They're not the most probable uncertainties. Now, unless the manufacturer specifies otherwise, we would assume that the uncertainty is normally distributed within the tolerance range. Now, to be honest here, not all authors agree on this. Some will say that the uncertainty is distributed via a rectangular distribution. Others will say via a triangular distribution, and then some normally distributed. But other authors have argued that The difference is not all that great between the rectangular, triangular, and normal distribution, so why not just use the normal distribution to keep it simple? That's what I'm going to do here. So the tolerance, remember, is the maximum uncertainty. It will include 99.7% of all the possible values, and this is x bar plus or minus 3 standard deviations. Whereas the standard uncertainty, the letter for that, letter symbol is U for uncertainty, not to be confused with mu for population mean. They look alike, but in context we can keep them straight. So the standard uncertainty, U, will include about 68% of all the possible values, that is x bar plus or minus 1 standard deviation. So to convert a tolerance to a standard uncertainty, simply divide the tolerance by 3, because 3 sigma divided by 3 is plus or minus 1 sigma. Let's try a problem. The most probable volume contained in a 100 ml Class A graduated cylinder with a tolerance of plus or minus 1 ml from the tables should then be 100.0 plus or minus 0.3 mils, because the tolerance divided by 3 is 1 mil divided by 3, or 0.33. Now I'm carrying an extra digit here just because I want to expand it later, but I would actually report the standard uncertainty as just being plus or minus 0.3 mils at the 68% confidence level. Then to expand this to the 95% confidence level, I would multiply by a coverage factor K of 1.96. So the uncertainty at the 95% confidence level will be plus or minus 0.33 times 1.96 is plus or minus 0.653, and I carried the extra sig fig just to show you that it does round up to 100.7 mils at the 95% confidence level. One more example. The tolerance of a 15 mil Class A volumetric pipette from the tables is listed as plus or minus 0.03 mils. So the most probable volume delivered by it would be 15 plus or minus 0.01. Where does this come from? We'll take the tolerance, 0.03, divided by 3, and we get 0.01 mils for the standard uncertainty. Note again that we are reporting standard uncertainty, which could be expanded using a coverage factor K. So plus or minus 0.01 times 1.96 would be plus or minus 0.02 mils. That would be the uncertainty at the 95% confidence level. So let's summarize what we've learned in this video. Systematic, also called determinate or one-sided or type B errors, lots of names, will bias or shift results, and they will affect accuracy but not precision, and they can be eliminated. Random, also called indeterminate, two-sided, or type A errors, will scatter the results, and they affect precision but not accuracy. Now, random errors can be minimized by repetition and averaging, and can be estimated by use of the standard deviation. A normal or Gaussian distribution describes the random uncertainty. Random measurements fall within x bar plus or minus 1 sigma 68.3% of the time, and within x bar plus or minus 1.96 sigma about 95% of the time. For single measurements, use the instrument tolerance divided by 3 to estimate the standard uncertainty. So you've completed standard uncertainty and instrument tolerances. That's part 3 of a 4-part video series, and you'll find links to the other parts. Part 1, Sig Figs and measurement uncertainties. Part 2, accuracy, precision, error, and difference. Part 4, combined uncertainty, that is the propagation of error, and other chem videos at the website www.chemrad.com. And thanks for watching.